Hey there, welcome to a video discussing the first two pages of section 5.2 on the mean value theorem for derivatives. So we'll start with an example. I hear that Mr. Amashi's Lamborghini can really accelerate from rest, traveling 330 feet in 5 seconds. Now I don't have a Lamborghini, I actually have a Infiniti G37. It's fast, but not as fast as a Lamborghini. So first off, let's actually calculate the average velocity for this journey. We've talked about average rates of change in the past. So average velocity is simply just going to be the change in your distance over your change in time. So clearly, if I travel 330 feet, that's my change in distance. And I do this over 5 seconds, it's my change in time. So I get about 45 feet per second. Actually, hold on a sec. 66 feet per second, my bad. Let me undo that because that's a little hard to read. There we go, 66 feet per second. Now, if you're curious what that would be in miles per hour, we could do a little conversion here. 44 feet per second is roughly 30 miles per hour. So this will be roughly 45 miles per hour. So that's going to be my average velocity for that 5-second trip in a Lamborghini. Now, will there ever be an instant during that journey when the actual velocity is this value? Well, yeah, of course, totally. And for those who are not familiar with Lamborghinis, typically you can accelerate to 60 miles per hour in about 5 seconds. So my instantaneous speed, probably at the end of the 5-second journey, will be more than 45. So the question is, will there be an instant during that journey when the actual velocity is this value? Well, yes, of course. Because I do have to hit 45 somewhere in that 5-second time frame. Here's another question. If Mr. Reyes, he's our assistant principal of academics and taught math, if Mr. Reyes drives continuously 130 miles in 2 hours in his Ferrari, will it necessarily at least one instance of speed will reach 65 miles per hour? Well, yes, of course. His average velocity is 130 divided by 2. But he probably doesn't travel 65 miles per hour the whole time. Maybe he might speed up a little bit. Maybe he might slow down. But he'll at least hit 65 miles per hour at least once. So given this, we can say with confidence the following, which is the mean value theorem for derivatives. If f of x is continuous at every point on the closed interval, so if you have a closed interval, so in this case, we're going from 0 to 5 seconds, or in this case, we're going from 0 to 2 hours for Mr. Reyes. And assuming you're continuous, so if you were to actually plot your position, if this is a position function, we use s of t, and that being t, there's not going to be any breaks there. And we're differential at every point in the interior from a to b in our interval. So we have a nice smooth curve for our position function. Then we can say with confidence that this is a true statement. F prime of c is going to be the slope of a tangent line in the interior of our interval. And this right here is going to be the average rate of change, as we've seen in the past. So what this means is that, let me actually get a text box, that might be a little easier. Let me type this up first. There will be at least one x value, which we'll call c, in the interval a to b when the instantaneous rate of change equals the average rate of change. Okay, now the text box should be visible. So that's what this tells us. So if this is from A to B, so let's say this is A. Let me change colors actually. Excuse me. That's A and that's B, and C is in the middle. So that's the tangent line. And if I drew a secant line connecting A and B, guaranteed there's going to be one tangent line with the same slope as the secant line. Let me actually clear, well, I won't clear just yet because I think you guys might still be copying. Let me actually do a better drawing here to really kind of drive this point home. So again, if I got some sort of funky curve like this, say this is A, say this is B, and if I connect those dots, then guarantee there's going to be a tangent line with the same slope as the secant line. That's what this tells us. So that's what geometrically is happening. That the slope of the tangent line, or the slope of this, there will be a slope of the tangent line equal to the slope of the secant line for that interval from A to B. And we do it from the interior because we want C to equal something inside, because we want to prove that there's something within A and B that will have the same tangent line as the secant line. Okay, so let's keep going a little further. So again, this is a position function off to the left here. And you're starting at 0, so you haven't traveled yet. And in 5 seconds, traveling through 330 feet. So this is the same thing about me driving a Lamborghini in 5 seconds. And after 5 seconds, I'm going really fast, right? Again, if you were to look up how fast a Lamborghini goes, in fact, I'll probably do that right now. How fast does a Lamborghini go in 0 to 60? So it says here it can go 0 to 60 in 2.9 seconds. So in 5 seconds, you're probably going even faster than 60 miles per hour. So those really fancy sports cars can sort of very, very quickly, and sometimes that's why people take them to those really high-end racetracks to push their cars to the limit. Anyway, so if f of t is the position of my car, and the graph is something like you see down to the left, then f satisfies the condition for the mean value theorem, and there will exist some time c in the interval from 0 to 5 when the slope at t equals c will be the instantaneous velocity does equal the average rate of change. So let me actually erase this drawing here, but what I just drew, that tangent line, was the speed at 5 seconds, which is going to be really fast, which might be like maybe 70 or 80 miles per hour if you were to solve that. But what we're going to do instead is if I were to connect the origin to point A, and that's a secant line. So this slope, again, is the average rate of change. Then the mean value theorem is telling us that there's some x coordinate c between 0 and 5 that will have the same slope as the secant line. So the slope is, in this case, instantaneous. Rate of change. If I found the slope of OA, well, that's easy. That's just 330, O's right here, the origin, minus 0 over 5 minus 0, which is going to be 66 feet per second. We already did this before. And geometrically, what this is telling us, let me get a text box out again. There will be at least one x value, which we'll call c again, where the tangent line is parallel to the secant line through your endpoints A comma f of A and B comma f of B. So now you can see the text box. And actually, let me select it so you guys can see a little better. So if you look at one more visual in the lower right corner here, so this is a secant line that's going through A and B. And in this case, we said there's at least one x value. Well, I probably could find several here. I could probably find maybe that one's going to be parallel. Maybe that one's going to be parallel. So I can find a couple between A and B. So we'll call this like C1. I could call this like, say, C2. I could find more than one tangent line that's parallel to the secant line. We have at least one. That's a guarantee from the mean value theorem. Okay, so that's page 1 of these notes. Let's talk about page 2 of these notes. Now, so the takeaway, if your hypothesis is not true, so what's our hypothesis again? That you have to be continuous on a closed interval and differential at every point in the interior from A to B. If it's not true, then we cannot draw any conclusion from MVT. So what happens if the hypotheses are not true? You can't say that f prime of C will equal f of B minus f of A over B minus A. So you can't draw that conclusion if you don't have the continuity differentiability hypotheses satisfied. So like, let's look at this curve here. This is obviously not continuous. And if you drew the secant line between A and B, here's your secant line. And remember, the slope of the secant line is given by this formula right here, which we've seen many times. Can I draw a tangent line on the red curve here, so that's parallel to the secant line? Well, no, of course not. There's no way I could do that if I'm not continuous. Here, we have a cusp, meaning that you're not differentiable. We talked about this. That's because the left-hand derivative does not equal the right-hand derivative. We talked about this many times in the past. The left-hand derivative is going to be, I think, positive infinity, and I think the right-hand derivative is going to be negative infinity, so obviously not differentiable. So here's your secant line, which obviously is horizontal here between A and B for this red curve. And I can't draw any tangent lines that are parallel to that. I'm not going to have any that are horizontal. So the hypotheses for the first graph here does not apply. And that's because we were not continuous. So therefore, there's not an x value that's going to be tangent to the there's not going to be a tangent line parallel to AB. And here, again, does not apply. That's because we're not differentiable. And again, there's not going to be an x value in the interval from A to B where the tangent line is parallel to line AB. Let's do some more examples. Again, now in this case, we do see a tangent line that's parallel here, and we do see one that's parallel here. Of course, this is not continuous. And of course, this is a corner. Well, I don't want to say of course, but it is a corner. So it's not differentiable there. So MVT, again, does not apply in each of those cases. However, there is a value that's parallel. There is a tangent line parallel to this line right here. Those are parallel. And those are parallel. So although MVT only just states the existence of C and not its value, we can let me take it back. I'm getting myself a little ahead here. So I think what I'm trying to say here is that MVT could work if continuity differentiability is not satisfied, but not guaranteed. So that's kind of the theory that goes into this. Now, let me talk about the next part here. Although the mean value theorem only just states the existence of C and not its value, so it just tells you that there is some value. It doesn't. We can figure out what C is by using the example below, and then we'll stop the notes there. And we'll pick it up on page 3 next time we meet. Show that the function is the inverse cosine of x satisfies MVT. Well, the inverse cosine of x, if you were to graph it, I'm going to go to Desmos in this case. Y equals inverse cosine functions, there we go, of x. So that's continuous. So here's -1, here's 1. That is totally continuous, and I don't see any corners or any like vertical tangents or cusps or anything like that. And that's differentiable in the interior from -1 to 1. So yes, mean value theorem does exist. So you could just make a quick statement that continuous on -1 to 1, or f of x is continuous and differentiable. Just make a statement. That's what it is. Make a statement. And then you can say, therefore, MVT for derivatives. And the reason I'm saying for derivatives, sometime next week, we're going to talk about integrals or integration. So yeah, there's another thing that we do in this class called integration. So we have another mean value theorem for that. But therefore, mean value theorem for derivatives will apply. Now, find each value C in which that is satisfied. So now you have to do a little bit of algebra here. So first I do need the derivative of this, which you may have forgotten. It's -1 over root 1 minus x squared. And in case you've forgotten, no worries. Actually, I had to kind of jog my memory a little bit for that one. Remember this cheat sheet, derivative rules and formulas to memorize? I'll probably put in the front of our Schoology page, but it's right here. Inverse cosine -1 over root 1 minus x squared. And actually, I'll replace x with c because we're putting c in for x. Equals, excuse me, f of 1 minus f of -1 over 1 minus -1. Well, you have -1 over root 1 minus c squared. Now, inverse cosine of 1, hopefully remember a unit circle, is going to be 0 radians. This is in radians, by the way. So please, please, please assume radians. Inverse cosine of -1 is going to be pi. And down below you get 2. So -1 over root 1 minus c squared equals -pi over 2. We will cross multiply. Negatives will actually cancel because you have negatives on each side. So 2 equals pi times root 1 minus c squared. I'll divide by pi. And then square both sides. So 4 over pi squared equals 1 minus c squared. Move things around, move c squared from right to left, move the 4 over pi squared from left to right. So c is going to equal the square root. It's actually plus or minus 1 minus 4 over pi squared. So I know it's kind of nasty, but that's what we get. So those would be the values of C that would satisfy that. And if you were to work that in a calculator, 1 minus 4 over pi squared. So let me do 4 over pi squared first. 1 minus that, square root. Yeah, you get 0.77. Plus or minus 0.77, which is totally within that interval. Then you're asked to find the equation of the secant line, AB, if A and B are the endpoints of the function. Okay, that should be pretty easy. Well, we already know the slope is negative pi over 2. So we go ahead and clear my drawings here. So we can use this. And we knew this was negative pi over 2 when we worked that out. So you have negative pi over 2. And you can use either endpoint. Like that was 1 comma 0. So you do y minus 0, x minus 1. Then you said find the equation of the tangent lines at x equals c and graph the function secant line and the tangents using the following window. Now, unfortunately, I need to renew my license for the TI emulator. So I'll just do this in Desmos really quickly. But the equation of tangent lines, now remember, C had equal plus or minus 0.77. And if I do f of those numbers, f of negative 0.77, or f of positive 0.77, so I'll do the inverse cosine of those numbers. Oh, let me try one more time because I was in radian mode. Okay. So f of negative 0.77 is going to be 2.45. And f of 0.77 is going to be 0.69. Actually, you probably should do 3 decimal places. So I'll say 2.450 and 0.692. So tangent lines will be y minus 2.450. Remember, my slope was the same thing, negative pi over 2. X minus, or actually x plus 0.77 because the x value was negative 0.77. My other tangent will be y minus 0.692. That's supposed to be negative pi over 2. Sorry about that. X minus 0.77. Okay. So now I'm going to go ahead and graph all that in Desmos. And yeah, just take a look at it and then we'll wrap up this video. So you have inverse cosine of x, which I already have here. I'll do my secant line y equals, we'll say negative 0.5 pi x minus 1. So you see that's a secant line going through the endpoints negative 1 and 1. Then y minus 2.450 equals negative 0.5 pi x minus, x plus 0.77. So you can see we have a tangent line that's green, touching it right there. And I'll do one more, y minus 0.692 equals negative 0.5 pi, in this case, x minus 0.77. And that's in purple. Let me clear my screen and let me zoom in just a little bit. So you can see the tangent line, the blue line, sorry, the secant line going through the endpoints. You see the first tangent line right there, and you see another tangent line right here. So that's mean value theorem in action. Okay, so I'll go and wrap up this video. There'll be a Google form and some textbook problems, worksheets to go through. And yeah, I will see you guys later.